Swayam Prabha. Digital India. Educated India.
Okay, good morning. My name is Ethayaraja Mani. This course on theory and application of stochastic process in chemical engineering will be taught in this slot E. I've given the schedule. So Tuesday 11 o'clock, Wednesday 10, Thursday 8 a.m. and Friday 5 p.m. So I've scheduled all 4 classes per week, but going forward I might cancel few classes because of some travel and other plans. So some classes may be cancelled. This course will be evaluated based on this pattern. The quiz 1 and quiz 2 each carrying 20%, and there is going to be a written form of end semester exam carrying 40%, and then project. This project is an individual project which will carry about 20%. This project is something you'll have to submit at the end of the course, and so typically you start working on the project in the middle of the course. Once we have learned enough topics and subjects, we can start working on a project. And here are my contact details, my email address and phone number if you want to reach out to me. So this course, the objectives of this course is to learn an unified introduction to stochastic process. I say unified because there are different forms of this subject being taught in mathematics and physics, and very little in engineering. So my objective is to bring those theoretical development in physics and mathematics and then apply to engineering, in particular chemical engineering. So that is the idea, and we also will talk about a very unique numerical technique called kinetic Monte Carlo simulation, which is a very powerful scheme to solve stochastic processes. Okay, so towards the end of the course we will do that. The content is actually made into 6 parts. First we will have some introduction on various background and probability theory, which most of you must be familiar, but we will quickly review these concepts so that we are all on the same page. And then we will start with the most simplest form of stochastic process known as Langevin equation, originally derived for Brownian motion, and then see some of the application of Langevin equation in other circumstances. And then we will proceed to a generalized framework on Markov processes, which is a form of continuous stochastic process. And then the chapter 4 is on master equation, which is also a stochastic process, but the events are discrete. It's called jump processes. Okay, so we'll talk about various aspects of master equation, and then application to a lot of chemical engineering related topics like chemical kinetics, bacterial growth, desorption, diffusion, and so on. And the 5th chapter is Fokker-Planck equation, and then it's also another way of looking at stochastic processes. And like I said, last one would be on the numerical technique, where you can devise an algorithm, a numerical algorithm to solve stochastic problems. There is no single textbook for this course, so I am suggesting some 3 of them because different materials are taken from different books. And apart from this, I will also share class notes at in the Moodle page. So right after the class, you can go and check. You can use that as more like a class notes for you to follow, and more information, more details can be obtained from these textbooks. So before we discuss about stochastic process, first let us understand what is mathematical modeling is, and why we want to do that. Okay. So we can kind of define formally that the mathematical modeling, it's basically it's a quantitative description of a natural phenomena. right? So what we are saying is a mathematical modeling is nothing but a quantitative description of a natural phenomenon. So quantitative means that we are able to even predict the actual occurrence, not only qualitative but also quantitative. You can say something in a quantifiable manner, something in a more accurate manner. So we say natural phenomena to keep the scope broader and wider, but within this you can talk about a chemical process, physical process, biological process, and so on. So, okay. Now the question is like, what do we want to do it? What's the motivation? What's the scope of doing such a mathematical modeling of a process? What do we want a quantitative description? Well, there are several advantages. I'm going to list a few. The first is a model, a mathematical model can suggest an outcome without really doing an experiment. Okay, so a mathematical model, if it is an accurate one, if it is a useful one, it can give you an information, an observation in the absence of actually doing an experiment. Okay, an example could be, let's say you want to look at nuclear reactions or impact of an explosion. So these are some of the phenomena. When it actually happens, the consequences are quite large, that instead of actually conducting a nuclear reaction or a explosion, one can build a model and then analyze what may be the possible outcomes. Okay, so during this Manhattan project, an estimate was made what would be the impact radius of this explosion, and based on that the experiment was held. So it's quite useful in that sense that we can predict to an extent what are the implications of a conceived experiment without actually doing an experiment. Okay, so it gives some sort of a guiding principle for you. This is one approach. Sometimes a model, a mathematical model, can explain the role or effect of a control variable okay. An example could be, you want to know how pressure varies as the altitude varies. Okay, so if you have a model, you can predict what would be the pressure at a higher elevation, and why that may be important. For example, let's say if you have seen this Maggi noodle advertisement, it says 2 minutes you can make a noodle. If you ever went to a hill station and if you ask for any noodles, a shop will take at least 15 to 20 minutes. That's because at the elevated heights, the pressure is low, boiling point is also low, the cooking time is more. Okay, so knowing this pressure versus altitude helps you to say what is going to be the boiling temperature, how much time you need to cook in a very simple way. Okay, and you can extend from here to some other issues also, where you want to look at how one variable affects the other variable through a model, and then you can analyze the implication of those ideas. A mathematical model can also save lives. Example, a climate model. If you have lived in Chennai for enough, you will know that every December, January, we are expecting a cyclone. We need a weather model to say what is the speed of the wind, what is the likelihood of the rain. So those are all coming from a climate model, and it actually allows us to kind of prepare for the adversaries. Okay, we can move to a safer place, or we can make precautions. Okay, so these can be obtained from a mathematical model like a climate model, or even so is epidemic models. Okay, a disease is broken, an epidemic is broken, and you want to see at what rate it's spreading, so that you can devise a public health policy to confine the spread. Okay, so from a public health policy point of view, a model is quite useful in that sense. Sometimes a mathematical model can also unify a large set of phenomena into a single principle or single equation or single model. Example would be Newton's law of motion, let us say. So here, whether you are talking about movement of celestial bodies or dynamics of molecules, you can still apply classical mechanics from Newton's law and you can predict the outcomes of the properties. Okay? So a very wide range of problems can be cast into a single principle or a single model, and that can also serve a lot of use. Okay? So these are all some of the ideas you can think about why one is interested to build a model. Okay? So I hope that with these examples that you may be convinced that the model is something that you can make one and then look at effect of these model and then try to understand what is really going on in a given process. Okay. Now, when we look at this modeling exercise, it is not like a it's not like a formula that you can start from one step to end step. Building a model is more iterative. Okay. If you look at any of this model building, you will see that we have to follow the rules of the physics, laws of conservation, symmetry principles, constitutive relations, and then laws of thermodynamics. So we know that through our experience that some laws have to be followed no matter what, whether it's a physical process or a chemical process or a biological process. Some laws have to be followed. Mass has to be conserved, energy has to be conserved, momentum has to be conserved. Okay. And second law of thermodynamics has to be conserved. So these are some of the constraints which we have to take into account. Then you apply these laws, and then sometimes you have to include some of the forces, whether gravity is important or whether electrostatic forces are important, whether van der Waals forces are important. Okay. So what is the nature of the external force acting on the system that you want to model? So the nature of forces, conservation laws, symmetry principles, boundary conditions, initial conditions, these are all the entire a zoo of concepts that you need to come up with a model. Okay. So this, if you are a chemical engineer, if you have done transport phenomena, what I am talking about you can really connect. Okay. Yet I wanted to give some 3-4 examples just to see that how do we go about modeling a process and see what are the outcomes and how do we approach this problem. In all these examples you will see, I will start with the conservation law and then I will actually simplify that based on the given condition, and I will go about solving it based on some initial and boundary conditions, and then final expression will be a model that will say how one variable is changing with respect to another variable or set of variables. Okay. So that is basically the end goal of doing the modeling process. So the first example is let's say we want to find the steady state velocity profile of a Newtonian fluid characterized by density rho and viscosity mu through a circular pipe of radius r at laminar conditions. So most of you must have done this problem in your transport phenomena or fluid mechanics. Okay, it's a very well defined problem. The nature of the fluid is given, the properties are given, the geometry is given, flow conditions are given. So it's a, and you also know the answer also. Okay, the profile is going to be a, what is the profile going to be? It's a parabolic velocity profile, right? So we know the answer. Okay, so now let's see what are the steps we are going to do to get to this answer. Okay, when we look at a problem like this, we recognize it's a fluid mechanics problem. Okay, and we know that momentum balance or force balance is a starting point, and that basically takes us to the Navier-Stokes equation, right? So we start with our Navier-Stokes equation. So u here is a vector, velocity vector, and g is the body force, the acceleration due to gravity. And you got a pressure gradient, viscous effects, inertial effects and everything, okay. So this is our general starting point, which you will obtain by doing a simple momentum balance onto a fluid flow problem. But now I have already mentioned it is a laminar condition, okay, and it's a Newtonian flow, all that, okay. So from here, we can apply all these assumptions, and what we actually get is a simple Stokes equation from here. Okay, so this is the governing equation that we want to solve. Okay, this is a more general equation, but we simplify this general equation for the problem that we have, and then you get this. So now the geometry is a cylindrical tube. So you can think of x here and r here. This is the radial direction. This is the axial direction, and then we have to know the boundary conditions. So this is a solid tube, solid wall, so no slip boundary condition. So ux is 0, and then it is also a circular tube. So at the midpoint, we have to satisfy the symmetry. Okay, the first gradient is 0. So you have two boundary conditions, and then you can express this Laplacian in cylindrical coordinates with only r as a variable, and when you do that, you basically arrive at an equation that shows that ux, that is the velocity ux is okay. So this equation that you have here, it tells you how as a function of r, the ux velocity varies. So it will be 0 by that equation, so that it satisfies the no slip boundary condition, and the derivative is 0 because here by symmetry it has to reach a maximum velocity at the midpoint. Okay. So this equation basically predicts this particular velocity profile. Now you can conduct an experiment so that you have a Newtonian fluid and then you have a laminar flow, and then if you do a particle image velocimetry PIV measurements, you will see that the velocity profile is pretty much parabolic. Okay. So the reason for giving this idea, this particular example, is that you see what are the steps we are following. We need to try to mathematically model a process. Here the process is a fluid flow through a circular tube. We start with the governing equation. Where do we get this governing equation? This is from some conservation laws. Okay, and then we simplify this conservation laws for this particular problem, and then we enumerate set of boundary conditions, and then we can analytically solve them, sometimes numerically also solve them. The fact that I am saying Newtonian is already taken into account. If it is a non-Newtonian, you have to go one step above this, and you have to express stress in terms of strain rate with the different models, and then proceed. So this is a well-known example, most of you can really relate. Okay. Now let's look at another problem. calculate the temperature of a solid sphere as a function of time we say that the radius is r, initial temperature is T naught, and the surrounding medium is at T infinity. This is again a very simple example from heat transfer. So, I have a solid sphere initially at some temperature T naught, and this is suspended in a continuous medium of air which is at a lower temperature, and we know that from thermodynamics that this object, solid object which is at a higher temperature than the environment will have to lose its heat so that it will reach a thermal equilibrium. Okay. So, now we are imposing the law of thermodynamics to say that two objects will have to be at thermal equilibrium when they are in physical contact, right. So, then what we are saying is we are going to write an energy balance. So, whatever the amount of heat that solid is losing, it has to be acquired by the air, and then we can write set of equations for this, and then we can look at it. So, in this case we can write a heat balance equation. So, we will get something like rho v Cp dt by dt is equal to H A T minus T infinity. So, what you see on the left hand side is the enthalpy change or the heat that is changed by the solid, and this is the amount of heat that is convected through some heat transfer coefficient. I hope that you are aware of how I write this. This is based on some Newton's law of cooling, which is based on area available for heat transfer coefficient, and then the thermal gradient. Okay. So, T here is the temperature of the solid as a function of time. Now, if you look carefully, I am representing the temperature of the solid as one single variable T, but where am I measuring it? If I measure the temperature inside at the origin or at the surface, it is going to be different, okay, because the solid has a finite thermal conductivity. There is going to be temperature profile within the solid body. My question was not that. I am only saying calculate the temperature of a solid body. So, I am referring to some sort of an average temperature then. Okay. If I have specified find the temperature profile within the solid body, that is a different formulations. I have to even solve heat conduction equation within the solid. That takes me to a fixed second law equivalent heat equation. But now for this case, I am only talking about an average temperature. At any point of time, I can find the average temperature of the solid, and I denote that as a capital T, and I am interested in finding out how T will change with respect to time T. Okay. I already have given all the other required condition for this. The initial condition is specified, and the boundary conditions for the air is also mentioned. So, all the other physical parameters are here. You can see the simple first order ODE, okay, with an initial condition specified. And if you solve this, you will see that the temperature of the solid body would exponentially fall and reach the temperature of the surrounding medium T infinity. Okay. So, it is an exponential decay, and the rate of this decay depends on all these factors. If the heat transfer coefficient is high, it will decay fast. If the area is more, yes, it is going to decay fast, and then it is inversely proportional to the heat capacity and the density and so on. Okay. It kind of gives all the relationship that you want. You want to look at the heating cooling of a solid sphere which is made up of iron versus another one made up of glass. It is going to have totally different rate of cooling, okay, but the profile will be the same. Both will be decaying exponentially, but the rate of cooling is going to be very different, because those are the parameters that's going to determine the time constant of cooling. Okay. So you can see that, you know, one simple model can tell me how an iron object will cool, or a wood object will cool, or a glass object will cool, okay, under similar conditions like this. So a lot of rich information can be obtained by doing this kind of model. So if I plot this equation, so here I have T minus T infinity by T naught minus T infinity. This is time, okay. So it will fall from 1 to 0. Like this, okay. So this is the equation. So this third example is a chemical kinetics problem, that you have a species A, and it is reacting to give species B. Initially you have some Ca0 concentration, okay, and then there is a rate constant K that is specified, okay. So the question here would be calculate the concentration of species A as a function of time, okay. So clearly this A is reacting away, so as a function of time the concentration is going to decay, okay, but in which way, in which manner, that's something one can try to model. So for a batch reactor, you will see that dCA by dt is written as something like this. Here what we are saying is, we are considering this as an elementary reaction, that's an assumption I have made, and the rate at which A is changing is proportional to the current concentration, okay, and then the initial condition is mentioned. How do you obtain this? This is something you can obtain by doing a mole balance, okay. Mass has to be conserved, so you do a mole balance on A, then you will arrive at this equation, and if I change the reactor from batch reactor to a CSTR or PFR, you would have another set of equation mimicking the dynamics in that particular conditions. So if you solve this equation with this initial condition, you will see that the concentration decays exponentially, and the rate K, which is a function of temperature, okay, and you can manipulate the rate of decay with different rate constants at different temperatures. So this equation tells you what is the quantitative information about the number of molecules of A or the concentration of molecule of A as a function of time. In addition, I can also predict how this will change when I change the temperature, because I can encode the temperature dependence of the rate constant through Arrhenius formula or Arrhenius equation. So you can see what are the additional information you can get, right. So that's the power of doing this mathematical model and analyze a physical problem or a mathematical problem. The last two examples are telling you about function of time. The first one was a steady state problem, okay. So it's already reached a steady flow. So you look at time invariant velocity profile. So you can have different ways. It's not necessary that all your model should be time dependent. You can also ask what is the steady state information is, okay. So again, it depends on, as a person, as an engineer, what is that you want to achieve, what is that you want to answer, okay. Based on that condition, you can always come up with this. But in all these examples, you would have seen that our strategy is describing a well-defined problem, okay. Defining a problem well is the first step, very important and very crucial step, okay. You have to give the enough information as possible. Then as a modeler, you would look at what is the starting point, what is the governing, what is the conservation quantities, and what are the governing equations, how much I can simplify so that I can make the model as simple as possible, and then the next step would be solving them analytically or numerically based on the initial and boundary conditions, okay. So and then you go out and then analyze what are the effects of various variables, okay. Like I said here, you can analyze the effect of heat transfer coefficient, effect of heat capacity, effect of the particle size, and so on, okay. Whereas here you can talk about the effect of temperature, right, and conditions like this. So that's really the power of this doing a mathematical model. Now, if you look at all these profiles, so here if I draw, this would be an exponential profile also, right, like this before. Okay, starting at Z naught, decays like this. All these examples I have shown here, these are called deterministic models. Okay, deterministic, what it means is certainty. Okay, so there is no confusion about the predictions. At time t, there is a well defined unique value that this variable will take. There is no uncertainty about it. Okay, so that's why it's called deterministic. Okay, it's certain that the concentration will be just this. Okay, so the question is that can we model all the physical problems in this way? Can we all predict deterministically the outcomes? I can give you some example where the response or the observation that you make can be very irregular, chaotic. Okay, for example, if you look at the trajectory of a Brownian motion, okay, a particle, a micron sized particle, a pollen grain suspended in water, if you look at it in microscope, you will see that the dynamics is very irregular, it's very chaotic. Okay, it doesn't follow a nice projectile kind of a motion, right, it is very chaotic, very irregular. Then you look at your favorite stock price over a period of a month or time, you will see that the prices are very fluctuating, there is no smoothness in the way it varies, right. Then look at look at the instantaneous temperature of Chennai over a period of month, you will see a lot of fluctuations, very irregular. Okay, so there are several processes in which the response is not as smooth and as new as these profiles. Okay, they are subject to a lot of irregularities, okay, lot of uncertainties. Now the question is, how do we take into account of those factors and how do we model those processes? Okay, so that's what brings us to the realm of stochastic processes. Okay, stochastic means random, it means chance. Okay, so how are we going to model problems, physical, chemical, biological problems where the outcomes are not certain, there may be multiple outcomes and a lot of irregularities. Okay, so that is basically the genesis of the stochastic process, and I think this field as such, stochastic process, became very famous and more prevalent since the since Einstein wrote this equation for Brownian motion in 1905. Okay, from then onwards, people looked at signature of Brownian like motion in other fields. Then wherever there was an irregularity and a chaotic motion, and they tried to bring in stochastic approach to model. Okay, so in here, what you saw was a nice change of concentration versus time. Suppose if I have a very small reactor where I have some 100 molecules. Okay, so when can I have such a case? If you're doing chemical reaction engineering laboratory in your course, you would typically deal with a few mLs, maybe tens of mLs, maybe hundreds of mLs of your reactions, few molarities. The number of molecules are of thermodynamically large. You're talking about 10 power 23 number of molecules. Okay, but there are some experiments where you can do at a very small reactor. Okay, a reaction within a cell, for example. Okay, or reaction within a droplet, and these droplets can be in picoliter volume. It can have a nanometer size. There are several objects in which the reactor itself can be nanometer size, and if you count the number of molecules that is there when you conduct a reaction, it can have hundreds, maybe thousands. And then if you look at as a function of time how the number of molecules varies, okay, in those small scale systems, you will not see this kind of a regular change. What you are likely to see is that the number of molecules in a very small scale reactor would probably start at some n naught, will stay for some time, and then it decreases by 1, and then stays for some shorter time and then decreases by 1, and then it stays for another long time and then decreases. So you will see some sort of step like discrete change over time. Okay, it is not going to be like this. Okay, so then the number of molecules at any point of time is going to become a probabilistic or a random variable. Okay, then the question is not about asking what is the concentration, but asking what's the probability of finding n number of molecules at time t? Okay, so that basically brings us to the realm of stochastic modeling. How do I recast this problem from a nice first order ODE into another framework where I can say what are the uncertainties in the specifications. So here there is no scope of telling you anything about uncertainty. Okay, it is a deterministic value. Okay, it's a fixed value, it's deterministic. But here in scales where the number of molecules are very small, you cannot have that opportunity to say that. You cannot definitely say the number of molecules at time t is this. You can only say from a probabilistic sense. You can tell mean, you can also tell what is going to be the standard deviation. You can associate an uncertainty to the mean value. Okay. So what we will show subsequently is that in this case, you can ask what is the probability of finding n number of molecules at time t. This becomes basically for this case, for a first order reaction like this, it becomes simply a binomial distributed variable. Okay. So here what we have predicted in the deterministic case was concentration versus time. In the stochastic approach, what we will be able to say is we can say what is the probability of finding n number of A molecules at time t, and that becomes a binomial variable, binomially distributed variable. Okay, and you can see this k here coming over just like the way it came here. This tells you the probability of having n number of molecules. This is a probability of not having the number of molecules of B. And from here you can show that mean number of molecule from here is simply n naught into e power minus kt. Okay. So as far as this equation is concerned, the mean behavior is same as what you predict from the deterministic variable. Okay. If you divide by volume of the reactor, you get concentration, and this equation the same. Okay. So what is the purpose of doing this kind of a stochastic approach? It of course gives you the mean description which will match with the deterministic approach. In addition to that, it will also give you fluctuations and standard deviation from this mean behavior also. That fluctuation you cannot get from this approach. Deterministic approach does not give you anything about the uncertainty. It does not give you anything about the fluctuations, but this approach does. Okay. So the most important thing to remember is the deterministic approach gives a single outcome with certainty, okay, whereas the stochastic modeling approach gives many possible outcomes with an associated probabilities. Okay, so that is the key difference between these two. Now, if you ask, when do we model a process deterministically and when do we do stochastically? The problem itself does not tell you what to do. Okay. It is about you, the modeler. What is that you want to ask? What is that you want to predict? It's based on our choice. In some level, deterministic approach is good enough. If you're asking, the kind of question only the deterministic approach can give you. In sometimes we want some finer details, some finer informations, and that cannot be given by deterministic approach, and then you have to do this stochastic approach. So the choice of which way to go is pretty much on us. We have to decide what is the approach we want to take. Okay, so that is one point. And the second point is that what are the scenarios typically you will apply stochastic approach? I can think of two scenarios. One is whenever there is a reduction in the dimensionality. And second is breakdown of continuum or thermodynamic limit. So by looking at all problems that people have studied stochastically, you will see that there are two scenarios where people would have actually applied stochastic approach. One is when there is a reduction in the dimensionality. Okay, what do I mean by that? When we try to project a larger dimensional information into a lower dimensional information, you will see the observation becomes very chaotic and irregular. Okay, an example is this Brownian motion. So what is really happening in a Brownian motion is that you have this large particle, and this is constantly being bombarded by the surrounding liquid molecules, the solvent molecules. The number of molecules hitting this object is so big, so large, okay, so that you are not able to account for individual effects. You say something about a collective effect of the solvent molecule hitting the particle. So when you reduce the number of dimensions, so here when I say number of dimensions, I am eliminating all the degrees of freedom of the solvent molecule. I am only saying what is the net effect the solvent molecules are imparting on the particle. What is the net force that is acting on it? So when you add up the individual elements together and give a net effect, you are basically breaking down the dimensionality. You are coming from a very large dimensional space to a small dimensional space. Then what is your observable? Your observable is a particle, okay, and the net effect on this particle imparted by the solvent molecule exhibits itself as a stochastic or irregular motion of the particle itself. Okay, but if you want to include all the degrees of freedom of the solvent molecule, you will do a simple classical dynamics kind of a picture, where each and every solvent molecule is tracked, the forces acting on them is tracked, the amount of force it is imparting on the particle is mapped, and you have to imagine how many number of water molecules you have to consider there. Okay, so that becomes a very, very detailed procedure, and the scope is not possible there. So what you try to do is you average, you look at the net effect of all the solvent molecules on this particle, and this is what I call as reduction in the dimensionality. Okay, the same thing with the climate model. We are looking at how temperature, pressure, and air velocity is changing, but that is actually affected by so many other variables. Okay, the local altitude, the population density, vehicular movement, various other natural phenomena that's happening, and we don't have possible way of incorporating all of them, okay, in a true sense, in a more physically correct formulations. So what we try to do is then we give only a net effect. What is the net effect of all these variables on pressure or on temperature or on other variables? So whenever you combine a very large number of affecting variables into a net effect, and it's very likely that the observation is going to be irregular and erratic, and then the response is going to be non-smooth. Same thing with the stock market pricing. Why it is so fluctuating? Because independent people are making independent decisions all over the world, all over the country, and there's no way we can understand who is thinking what. Okay, the net effect is seen on this stock price, and that is that's why it looks like very chaotic and irregular. So that is one area where we can think that the reduction in dimensionality can lead to irregularity, and that can be perceived as a stochastic process. The other possibility is breakdown of thermodynamic limit or continuum limit. the chemical kinetics example I said, where you're having a very limited number of molecules, and if you look at how A is coming into B, if you look at the dynamic, the molecular picture, what is happening is that there's an energy barrier each molecule will have to circumvent to become A to B. Okay, there is a potential energy surface they have to cross, and that is not a very smooth process. They are not ballistically moving and to cross it. Okay, so it becomes a very activated process. Few molecules have acquired enough temperature, enough kinetic energy, so they can jump, others cannot. So if you look at a very small time scale, you see that the number of molecules jumping over the potential barrier is not a regular well-behaved dynamics. Okay, so because of that, you see the number of molecules changing with respect to time is stepwise or discrete or not smooth. Okay, so you can imagine that most of the problem that we discuss in the course, the rest of the course, will probably come about in either of these two categories. Okay, and many times it is also depend on what kind of scientific development we make to observe things at a very, very small or minor molecular scale. Okay, so based on that we decide. So with that, I hope that I kind of briefly told you what is mathematical modeling, what is deterministic modeling is, and what are the things we can achieve. And then I also contrasted with the stochastic approach or stochastic modeling, where the outcomes are not deterministic, there is some sort of uncertainty, and what are the reasons and why such fluctuations may come. And the rest of the course is all about developing various theoretical tools to address such problems and then solving them. Okay, so we'll stop here.